those of you who don't know me, I'm Grant Martin. I was in the club. Let's see, I think it was 2 years ago was my last year. Did rabbit and dairy, so props to anyone out there in those groups. I just finished my first semester in college. I'm at Whitman College out in Washington studying astronomy, and so Hannah told me that for a program I should do a presentation on astronomy, so I said, why not? So, let's see here. So, these two pictures up here, they're the same thing, which obviously seems kind of weird. They're both called the Cat's Eye Nebula. Now, a little bit of information about it. It's you can see the little shells of gas, or like it's easiest to see on the left side. So you have that little thing in the middle is a star. It was about the size of our sun, and toward the end of its life, they get really big and then lose a lot of the energy that they have at the core. So they end up losing a lot of their mass, and that's what all of this stuff is. It's layers of like the outside of the star that get pushed out when it runs out of energy. And then the little star that's left is called a white dwarf, and it lights up all the gas with really strong radiation of all sorts. The cool thing about this is that they're the same picture, like they're the same object, just taken with different wavelengths. So the one on the left is taken with visible light, and the one on the right is taken in infrared. So you a lot of times when you see like night vision cameras or like heat sensing cameras, they use infrared light. So basically all that is the wavelengths given off by heat. So the brighter the color, like at the center you see the blue and the white there, and you see on some of the inner stuff, and then it gets darker, that shows light to dark. So the brighter the color, whites and blues give off more heat than the reds and the greens. So here's part of the light spectrum. So if you go back here, the picture on the left was taken invisible, which is this little part right here. The camera was able to capture the light wavelengths from around 375 to almost 800 nanometers. That's the visible spectrum. And then the one here on the right was captured in infrared spectrum here. And so it's really cool because they can scientists develop cameras that can take pictures in infrared, and that allows for people to take spectrographs, which they're basically an analysis of the way the light's reflected, and it's reflected differently based on the composition of the materials in the star. So basically by taking a look at this picture, we can figure out, based on the visible and the infrared picture, you can distinguish like what it's made of, which is really fascinating. Obviously it's more accurate when you get into ultraviolet and X-ray as well. Just gives you more information with composition stuff. But here's another picture of the very center of our galaxy. It's kind of low resolution, which is unfortunate, but here in the very center, there's a white dot, and that's the very center of our galaxy where there's so much heat and just material being thrown around by the massive black hole at the center that you can see in an infrared picture all of the bright colors, and that just is like all the heat signatures being given off from all the really hot stuff at the center there. So, as we know, it's space, it's huge. There's a lot of really big things. So, here's a galaxy. And to help scope out the size of this galaxy, from there to there is roughly 100,000 light years. Now, when you think light years, you don't really know how far that is. So to put it into perspective, in 1 second, a ray of light travels 300,000 kilometers. So you do 300,000 times 60. That's how far light will travel in a minute. Multiply it by 60 again, and you get hours. Multiply by 24, you get a day, times 7, week, and then times 52. That's 1 year, and that's 1 light year. Then you have to multiply that by 100,000 to get it all the way across. So it's basically so big that like you can't imagine how big it is. Similar to that, this is a picture of what's called the Eagle Nebula. So differing from the previous ones, those were planetary nebulas, and that just means that they're created from a star they're a lot smaller because each one of these little dots on that picture is a star. So your planetary nebula wouldn't be much bigger than one, but this is so big, it creates all of these stars. So nebulous gas falls together to create stars. That's how the sun was created, how basically every star is created. So that gives you the scope of the size of this massive gas column, because each of those tiny dots is a star that was most likely created from the material in that gas pillar. So yeah, I mean, there's a lot of stars there. That's obviously massive. So we get some funny stuff as well. This is a black hole, a picture taken of it, and it's invisible. We don't actually see the black hole itself. So a really interesting thing about black holes is that the light particles, they're called photons. They're basically little packets of light, and that's what we're seeing when the lights are on. It's photons bouncing off of objects and reflecting back to our eyes, and that's how we see. The funny thing about black holes is their gravity is so strong that it takes the tiny amount of mass that a photon has and still sucks it in. So they actually emit no light. You get this interesting warping effect around the outside here from the light bending as it gets close. So if it's close but not too close to get sucked in, it'll change the path of the light as it goes by the black hole. So that's why you get this really weird lensing look. And I wish I would have got a little video. They have time-lapse videos of a black hole just moving across the background light, and it creates these super cool arcs of light that just go all the way around it. So the light you can't see is light that gets too close to what's called the event horizon. That's the area where if light gets that close, it won't be able to come out and you won't get any of it back to your eyes. So basically, this is an invisible dot. It just looks black because there's no light coming back to us. And then, of course, there was a lot of funny math that we had to deal with. So this is Kepler's third law, I believe. It's basics for planetary motion. So this equation, for example, has to do with the time of an orbit. So what you plug in here, I mean, it looks pretty complicated, but it's actually fairly simple. You're given the variables. So 4 pi squared is just the makes it a circle. So that's how you know that you have a circular orbit. The big G on the bottom there, this is the gravitational constant developed by, I believe it was Newton, which is 6.67 times 10 to the negative 11th power, and that's always what G stands for. And then M in most cases with our solar system is 1 because it's solar masses. Basically the bottom half of this formula is just multiplying the gravitational constant by the mass of whatever you're looking at that is the center of mass. So if you were looking at one of Jupiter's moons, for example, your M would be the mass of Jupiter. So like for Earth though, it would be the mass of the sun because we're finding our orbit around it. And then A cubed is just the distance, how far it is away from the sun. So you plug all those in, you can pop out the time for your orbit. So it's pretty, that's very helpful when you're finding like, with the discovery of Pluto and stuff like that, people were looking for something way out there. And so you would know that your T would have to be really high because it's so far away from the sun. It has to travel so far to make one orbit. So when you're looking for objects out there, it's way easier if you can pick out ones that have a super long orbit and not just background stars. And then last little thing here, here's a picture of a meteorite, and what we did several times actually was we used hypotheticals to date different meteorites. So this is the formula we use. It's pretty hard to see, but you have a constant up top and T to the 1/2, which is just half-life. So you get your initial and final half-lives, and you plug them into that, and you can figure out how old an object is. So normally, when looking at meteorites, the ones that we try to date have high contents of strontium and rubidium, and strontium decays into rubidium with a half-life of 4.5 billion years. So those are the ones we look at with these formulas. So you'll find, scientists will go to like Antarctica, for example, and find a meteorite. They'll get it, take an analysis, find the ratio of strontium to rubidium, and then plug it into this formula, and it'll pop out the exact age of the rock. It's a little iffy sometimes because like this rock, you can just tell by looking at it, it looks like it's made of a bunch of other rocks. So chances are that earlier in the solar system, this got smashed into an asteroid and mixed around and whatever materials that had, and then broken out when it got hit by another asteroid. The ones that are really accurate for early solar system dating have little bits of glass in them called chondrules, and those are, it's kind of a giveaway because glass melts fairly easily. So when you have a little chunk of rock that has glass in it and gets smashed into an asteroid that's still molten most likely, all the glass is going to melt, you're going to end up with something like this. But with asteroids that have bits of glass in them that we find, we know that that hasn't had very much tampering as it's flown through the solar system over the course of, you know, however long, 4.5 billion years that we've been here. So it's really cool to look at these rocks because the ones with the glass bits and stuff, we've got pretty accurate readings for how old the solar system actually is. And that'll do it. So are there any questions?
Why Antarctica?
There's a lot of contrast there, and also because dirt cycles a lot, like something lands in the dirt and within, you know, even 100,000 years it'll be gone, cycled through with plate tectonics and stuff like that. And Antarctica is just a sheet of ice, so something hits it and there's not very much precipitation there, so it's just going to sit in the ice, and there's usually high contrast because the ice is white and they're usually pretty dark colored.
For the black holes, so is it really a hole or is it something else that we just don't see?
Well, that gets pretty complicated because with the whole space-time thing, it's easy to think about if it's like a sheet of like rubber kind of, and you set a ball in it and it bends it down. That's what gravity does. So like our sun would have a bend and a galaxy would have a way bigger one, but people theorize that black holes in that case would go straight through and make the actual hole to somewhere else.
Okay.
It's pretty funky stuff. I don't
Okay.
know. Yeah.
How big is the average meteorite?
I don't know, like on Earth, you don't get very big ones just because they would have caused like mass extinction and stuff like that, but there's, usually they're pretty small, you could fit them in your hand, just big enough to make it through the atmosphere and not burn up, because the friction with the air as they enter going super fast will usually just break them into little bits and they'll burn up, but some that are big enough make it through, and usually those are about the size of your hand when they land.
How do you calculate the mass of Jupiter and its stars?
Well, so there's a whole bunch of stuff out there for it, but mostly, like, people originally figured it out by looking at how much it affected all of the objects around it. So it has moons, and so you can calculate the size of the moon when it crosses Jupiter. Just by distance over time, you can figure out how wide Jupiter is, and then you can find the size of the moons using the same concept there. And then based on the speed that you would see the moons going around, and you know the size, then you could work some math in there and figure out how much. Yeah, it's really complicated. Anything else? Right on. Well, thanks guys. This